Well, I lied. We're not actually going to be doing any definite integrals quite yet because we need to learn how to work with the summations before we do some of these things. So I have a couple of summations I need to look at to see what they do. First of all, the sum I equals 1 to n of 1. Literally, this means, notice that the 1 doesn't depend on I. So I've got a sum of 1 plus 1 plus 1 plus all the way up to 1. There's n ones being added together, so that adds up to n. Okay. Next, the sum I equals 1 to n of I. All right. Now this does depend on I. Now when I is 1, this looks like a 1. When I is 2, it looks like a 2. Add them up, plus 3, plus 4, plus all the way up to n. Now this is equal to n times n plus 1 over 2. Now I see that this way. Here's 1, here's 2, here's 3. Let's just do it for n equals 4. Here's 4. Now I'm going to pick another color here just to distinguish this. Here's 1, here's 2, here's 3, here's 4. Now how many dots do I have total? Well, they're all in a rectangular arrangement here. It's 4 by 5. So I have 4 times 5, but I really have twice as many dots as I really wanted because I wanted just the blue ones. So take that and divide by 2. Right? The thing is, I used it with n equals 4. So there's 4 things going this way, but it was 5 going that way because I had that extra 1 repeated down there. And then, then the 2, 3, 4, and so on. So I make a rectangle, but I really wanted the triangle. So I get the area of the rectangle divided by 2. N times n plus 1 over 2. Okay. Now, next one. The sum I equals 1 to n of I squared literally means 1 squared plus 2 squared plus 3 squared plus and so on all the way up to n squared. This one's much less obvious. It's n times n plus 1 times 2n plus 1 all over 6. Let me see if I can show you a quick proof of that. All right, so what I have here is a stack of red blocks. In the top row, there's 1. In the second layer here, there's 4, 2 by 2. The next one, there's 9, 3 by 3. The next one, there's 16, 4 times 4. So this is 1 squared plus 2 squared plus 3 squared plus 4 squared. I'm trying to figure out how many blocks are in that stack. Then what I have is some other copies, 1, 2, 3, 4, 5 other copies of exactly the same thing. And what I'm going to do is I'm going to take those things and I'm going to bring them all together, and when they're all together I'm going to stop and say, okay, let's count how many there are. Now it's not immediately obvious that there aren't any gaps in there, but you can take them apart and look. There are no gaps. This fills this block completely solid. And so what I see with n equals 4, that across this side right here is 1, 2, 3, 4. Across this side is actually 5. 1, 2, 3, 4, 5. And going up and down, I've got 4 and 4 and 1. So this is 4 times 5 times 9. If I let this go a little bit further in my process, it's n times n plus 1 times 2n plus 1. That's the number of blocks in the whole thing. I only wanted one of those, and there's actually 6. Right? There's 6 things coming together, and I only wanted one of them. So n times n plus 1 times 2n plus 1 divided by 6. Okay, so next, the sum I equals 1 to n of I cubed. So this is 1 cubed plus 2 cubed plus and so on up to n cubed. This one is equal to n times n plus 1 all divided by 2, that's what that one was. Take that and square it. Right? I got a proof by picture of this one as well. I don't want to take the time in this video to do it. Ask me in class and I'll draw you a beautiful picture. Next, I need to be able to use the fact that the sum I equals 1 to n of c times ai equals c times the sum I equals 1 to n of ai. That is, if I'm just multiplying everything by a constant, I can factor it out. This is normally what we would call the distributive property, because literally this right-hand side, I'm going to rewrite that, sorry, this would be the left-hand side. The left-hand side means c times a1 plus c times a2 plus c times a3 plus and so on up to c times an. Well, the distributive property says you can pull the c out. a1 plus a2 plus up to an. So that's what this is, that you're adding up all the a's first and then multiplying by the c. So that's just the distributive property. Next we have essentially what is the associative property and the commutative property together. I got the sum I equals 1 to n of ai plus bi. And what I can do here is I can just add up the ai's first and then add up the bi's separately and add the results. Right? Again, this piece over here means a1 plus b1 plus a2 plus b2 plus all the way up to an plus bn. Well, this is all addition here, and so it doesn't matter how you have them grouped or what order you put them in. So let's rearrange them and put all the a's together. This is a1 plus a2 plus up to an plus, and then now all the b's. b1 plus b2 plus up to bn. And so this first part is that sum right there, and the second part over here is that one right there. And so it's just the associative and the commutative property, essentially, that allows you to break sums up like that. Okay. And the book also gives this with a minus sign in between, and you can put a minus sign in between. It's really not too hard to see that if all of these things have minuses in them, then all the b's would have minuses in front of them, and you factor out a -1, and so that would become a minus sign right there. Anyway, I don't really like to put that one as a separate thing because it's kind of a combination of these two. So anyway, we're going to now use those formulas to do some definite integral calculations.